In this problem, we're going to look at how much the force at the end of a cantilever beam might scale with changes in the dimensions of that beam. And again, we haven't done the physics or the mechanics or the derivations yet, just giving out some scaling laws that we can use to get an idea of how the loads that these different structures, bars and shafts and beams might be able to handle. So we have a cantilevered beam with a width of ½ inch, a thickness of 0.25 inches, and a length of 10 inches, which can currently support an applied force of 10 pounds at its end. Now, if we make these changes where we have a new width of 1 inch, a new thickness of 0.5 inches, and a new length of 8 inches, how would the load that this beam can withstand change? And one other thing that we want to keep in mind is that we want to go from 10 pounds at the end to force in newtons. Okay? So maybe drawing a little picture here is helpful. This is a beam, it's cantilevered against a wall. This is my poor drawing where you have a force and then you have B, which is what we commonly use to describe the width of a beam. H is what we often use for the thickness of a beam. And L is the length of the beam to the wall. And F is being applied at the end. And using the scaling relationships that are in the slides and that we talked about in class, we have that the supportable force is going to scale with h squared, b, and inversely with the length. Okay? So now we write out our algebraic equation describing these ratios. We have our old force times the ratio of the thicknesses squared times the ratio of the widths times the ratio of the inverse lengths, okay, as you see here. And when we plug in the numbers, so 10 pounds, and we do a conversion, so we're going to be going into newtons, so we have 4.45 newtons is equal to 1 pound, and we have this ratio of the thicknesses squared, ratio of the width not squared, but just linear ratio, and inverse ratio of the lengths of this beam. And we get the resulting force that we can support. Now, once again, why don't we go ahead and do this in Colab? Because there are a lot of numbers here and maybe there's going to be an error and maybe the numbers will change or we want to, check things out. So what we can do is open up a new Colab as we see here. Okay, and we'll right click, hopefully. Okay, right click, there it is. And we create this new Colab file that we open up, and maybe we can call it supportable, I don't know, we'll say beam load geometry, okay, like that. And the first thing, again, is that we're going to import the NumPy as NP, and we can go ahead and run that, and then create a new cell for the code. And we have an F old, and that was specified in our problem as being what? 10 pounds, okay? And I'm going to go ahead and multiply that by 4.45 newtons per pound, okay? And that is going to give us a resulting unit of newtons. Then we have an H new, and that was going to be, let's see, 0.5 inches. Okay, and again, it's often helpful to keep track of these dimensions. And H old that we had originally was 0.25 inches. The hold, that's fun. Okay, never mind. Okay, we have B new, that's the width, that was a 0.5 inches. And we have B old, bold, which was, oh wait, did I just make it, so B new actually is, yeah, 0.5, B old was 0.25. I think I might have made a mistake already. No, B new is 1. See, I have to, this is where it's helpful to write it out sometimes. B old is 0.5, like that. Okay, and this has units of inches. The L new, okay, is 8 inches, and the L old is 10, I think. Yes, 10 inches. Okay, and it's not liking that. Okay, now we do this. All right, like this. Okay, so now we can write out F new is equal to, I guess we can do nice spacing, F old times, now this is going to be a ratio H new divided by H old. Okay, and I hope old is not like a, it might actually be a dedicated parameter. So we'll see. We might have to change some things, but hopefully it'll work. We have B new over B old, okay, bold. So this is where underscores might be helpful to avoid issues. Now I could be lazy or I could be less lazy here, as this is the inverse ratio of the lengths. I'm going to be lazy, all right, but here we go, 1 over L new, okay, and then I'm going to be very careful though and add another parentheses, 1 over L old, okay, and I balance out my parentheses, okay, and this is going to have units of newtons, and then we're going to print the F new, and we're going to do a little rounding, maybe. This time I'll just do a 0 round for the F new. Okay, so 0 decimal places. Let's see how that turns out. And this is going to have units of newtons. All right, hit Control Enter, bada bomb. So even though I put a 0 there, okay, it still put a decimal point. All right, I put it in, whoops, like that. Let's hit Control Z because I didn't like that. Okay, like that. It's still there. I can go 2 decimal points. Okay. Actually, why? Oh, it's just because it comes out to be 445. I think exactly. Yes, it does, because it's what you see here is that this whole ratio ends up being a factor of 10, and it's going to be 445. Uh, so it went from 44.5 to 445. So it doesn't really matter now. But maybe if I change this number a little bit, if I go to like 11, all right, let's see what happens. Do I get, whoops, I once again, I change it, 489.5. Let's do 11.1. Yeah, so now it goes to 2 decimal points. So, if it ends at a particular decimal point, there's no additional information there, then it just ends it right there. Okay. Well, anyway, I hope this is somewhat helpful to be able to see how the load that a beam can support is dependent on its geometrical parameters of length, thickness, and width. Thank you.